In this video, we'll be going over how to define a spacecraft body fixed reference frame in the Spacecraft JSON catalog. The scene on the left shows the spacecraft body pointed in a local vertical, local horizontal, or LVLH frame, and on the right is a spacecraft tracking the sun with its solar panels. And as usual, we've added the scene scripts in the GitHub repository in this directory. The two scenes in this video are exactly the same as the one in the previous video, except for the body frame definitions in the spacecraft catalogs. So here we have the LVLH scene on the left with the spacecraft catalog on the right. So just like the video on defining the Earth-Moon rotating reference frame, when we define the LVLH frame here with a primary and secondary vector in Cosmographia, we don't define it exactly as it should be, with the secondary axis pointed in the direction of the angular momentum vector of the orbit. But since this orbit is nearly circular, this definition using the spacecraft position and velocity vectors is very close to true LVLH. Here we define the negative z-axis to be pointing from the spacecraft to the Earth, which is the nadir direction, which we can see in the scene where the Earth vector is pointed opposite of the spacecraft positive z-axis. And we define the secondary axis for the x-axis to be pointing the spacecraft's velocity direction with respect to Earth. And since this sun-synchronous orbit is nearly circular, the position and velocity vectors are always nearly perpendicular to each other. Now for the sun-pointing spacecraft, we define the spacecraft positive x-axis to be pointed in the direction from the spacecraft to the sun, which we can see in the scene here as those two vectors are aligned. And here the secondary we define as the spacecraft negative z-axis to be aligned with the y-axis of the inertial frame, and we'll go over why that is next. So we need to be careful about how we choose these secondary axes when defining reference frames with two vectors, because if we do it incorrectly, the reference frame will do a 180-degree flip about the primary at certain times. Here's an example where we define the primary x to point at the sun and the secondary z to point towards the velocity vector. So since the x-axis is defined as a primary, the spacecraft is allowed to rotate all around that axis in order to minimize the angle between the body's secondary axis and its target. So in this scene, we see that the body z-axis is rotating away from the velocity vector, and right as it's about to cross the 90-degree mark, the spacecraft does a 180-degree flip around the x-axis, which is the primary, so that the z-axis is now rotating towards the velocity vector, so its value is decreasing from 90 degrees. So for that reason, it sometimes requires some trial and error to pick a proper secondary axis that will prevent this from happening. So that's it for this video, and in the next one, we'll get into how to create planetary flyby scenes like this one, which is the Voyager 1 flyby of Saturn.